So till now, we have proved logistic regression. We have derived the whole idea of logistic regression itself using only geometry, right? We have derived the whole idea of logistic regression using geometry and simple algebra and some simple algebra, right? Simple algebraic transformations. Now there is another way to arrive at logistic regression. So there are actually two other ways of arriving at logistic regression. This is the first way that we approached because geometry and simple algebra are easy to understand. The second way to arrive at logistic regression or to derive logistic regression is using probability, is to use the basics of probability. The way we saw in naive Bayes, we can use very, very simple ideas in probability and derive logistic regression. There is a third way, which is called the loss minimization framework, the loss minimization method of arriving at logistic regression. So we have seen this first approach, right? We have seen this first approach. In this video, I'll give you an introduction to the probabilistic interpretation, and I'll give you some external pointers where you could, it's very, very simple. These external resources are very well written, where you could read up and derive everything step by step, very rigorously. In the next few videos, I will also cover the loss minimization interpretation of logistic regression. So by the end of this chapter, you will have the geometric interpretation, the probabilistic interpretation, and loss minimization interpretation. Oftentimes, a given textbook, if you pick any textbook of your choice, it either covers the geometric interpretation or the probabilistic interpretation or the loss minimization interpretation. So we try to cover all three of them so that you have a complete 360-degree view of logistic regression and understand it thoroughly from all three perspectives. Personally speaking, I have not come across any textbook which gives all the three interpretations in a single chapter or even in a single book. Personally, I may be wrong here, but that's my gut feel. That's my bet that there are very, very few books, or there is no book which covers all three interpretations. But they're important to understand, right? So now let's go into the probabilistic interpretation. So let's go into the probabilistic interpretation or the probabilistic derivation. Let me not call it interpretation. Let me call it probabilistic derivation. Probabilistic derivation of logistic regression. I'll call logistic regression as LR just for short, right? Remember, we saw naive Bayes, right? We saw naive Bayes in the previous chapter, right? So in naive Bayes, if your features are real valued, right? You can assume that your features, the conditional probabilities on your features are Gaussian distributed, and this is case 1, case 2, so not case 2, this is point 1, and point 2 is your yi is either +1 or 0, two class labels. So you can think of your response variable or your class label as a Bernoulli random variable. We looked at Bernoulli random variables as coin tosses, right? When you have a coin toss with only two outcomes, such a random variable can be thought of as a Bernoulli random variable, right? So in probability, if you take the naive Bayes approach with only two assumptions, the first assumption is that all your real valued features are Gaussian distributed, all the conditional distributions are Gaussian distributed, and that your response variable or your class label is Bernoulli random variable, then you can derive the whole logistic regression using first principles. Okay, so let's go to, so there's a very, very nice, I'll provide the link here in the description of this video. So there is actually a very nice book by a professor called Tom Mischel at Carnegie Mellon University. A very, very nice book, a very, very good introductory textbook for machine learning. In one of his notes, he actually literally derives the whole idea of, so if you look at this chapter, I'll provide this link. This whole chapter here is called, don't bother too much with the equation. It's called generative and discriminative classifiers, naive Bayes and logistic regression. He first explains you the whole naive Bayes concept, and then he extends naive Bayes to prove or to arrive at logistic regression very gracefully, right? So the way he does it is this. Okay, let's go through some of the. So the section 3.1 is where he derives it very gracefully. So if you look at it, he says your class label is Boolean, right, which is governed by a Bernoulli distribution, right? if each of your data points is x1, x2, xn, here he is using x1, x2, xn as n features that he has. Now the only assumption, so this is assumption 1, right? The assumption 2 that he's saying here is the conditional probability. Probability of xi given a class label is Gaussian distributed, is normally distributed. That's what I meant here. That's what I meant here. What I meant here is your features are real valued. If your features are real valued, you're assuming that the probability of xi given yi is normally distributed with some mu I and sigma I. Right? If that's the assumption you're making, and for all I and j, xi and xj are conditionally independent. This is the naive Bayes assumption, right? If you make these three assumptions, right, you can very easily in this section, if you go step by step, very, very simple algebra and simple probability, you will arrive at logistic regression formulation. You'll arrive at a formulation which is exactly your logistic regression formulation, right? What is this? Now let's look at this. What did we arrive at here? If you look at this formulation, let's discard W0. W0 is nothing but the, so if your hyperplane is W transpose X plus B, right? Then W0 is this B, right? So initially we said, let's discard B because we can always add it. So if you just discard this, what is this? So your probability of y equals to 1 given x is nothing but 1 by 1 plus e power W transpose X, right? This is nothing but sigma of W transpose X, isn't it? This is what we told as the probabilistic interpretation of why we are using the sigmoid function. So you can arrive at logistic regression very, very easily by just making these simple assumptions. So if you want to think about from a probabilistic standpoint, your logistic regression is nothing but is equivalent to Gaussian naive Bayes plus Bernoulli class labels plus Bernoulli distribution. So your logistic regression is a combination of these two. If each of your conditional probabilities of xi given class label are Gaussian distributed, assumption 1. Assumption 2 is if your class label is Bernoulli distributed, you can easily derive logistic regression trivially using a bunch of simple algebra. And for those of you who are interested in the proof, I will not go into the details. Please go through this. I'll provide this link in the description of this video. Please go through section 3.1. If you have time, I recommend you go through this whole PDF. It's a very, very well written PDF by Tom Michel at Carnegie Mellon. A terrific book that he has, a very, very good book he has. Okay, so that's how. So naive Bayes. So in a nutshell, logistic regression is nothing but Gaussian naive Bayes plus Bernoulli. So what is Gaussian naive Bayes? This is the probability of xi given yi. This is a conditional distribution, and Bernoulli if your yi is Bernoulli. If your yi is Bernoulli, then you get logistic regression, right? So in some textbooks which are more heavily oriented towards probability, again, each professor, each teacher, each person has their own preference. I prefer geometry personally because it gives me much more easy understanding of what's happening. There are some people who prefer probability. Those people typically end up deriving logistic regression using Gaussian naive Bayes and Bernoulli assumption on class labels. It's very, very simple, right? Now, there is one thing that you might notice. Look at the formulation that we wrote. The formulation we wrote was W star equals to argmin summation I equals to 1 to n log of 1 plus exp of minus yi W transpose xi plus regularization, right? Plus some regularization. This is what we wrote it as. So here you will notice that this yi, this whole in the geometric interpretation, remember, this is what we got from the geometric interpretation of logistic regression. Here yi is plus 1 or minus 1, right? If you follow textbooks which have probabilistic interpretation, you will not see this form. You'll see a slightly different form, which is W star equals to argmin or the W that minimizes sum of I equals to 1 to n minus yi log pi minus 1 minus yi log 1 minus pi, where pi equals to the sigmoid function of w transpose xi. This is what you'll see in some textbooks. Okay, here in this case, your yi is either +1 or 0, because in probability, in the probabilistic interpretation, you're taking +1 or 0 as your class labels. In the geometric interpretation, we took +1 or -1 as our class labels, right? So in some textbooks, you'll find this formulation. In some textbooks, you'll find this formulation. This is what you will arrive at if you're using the probabilistic way of deriving logistic regression. If you look at the geometric way, you'll come at this. This is what we did, right? Of course, this has plus regularization here, which I just missed out. Now I will show to you very quickly and elegantly that both these formulations are the same. Right? I'll quickly show this to you. It's not very hard. It's actually very simple algebra. Okay, so let's go through the proof and see it quickly. It's not very hard actually. So let's go to case 1. Right? Case 1 is when yi is positive. When yi is positive. When yi is positive, what happens in the geometric interpretation? Your yi is +1. What happens in the probabilistic derivation? Your yi is also +1. Right? So this is the probabilistic equation. This is the geometric way of getting it. I'll show that these two are equivalent. Okay. So in the geometric part, what happens? What happens to this term? Let's ignore regularization for now because it is independent of the formulation. In both formulations, you have regularization. In both formulations, you have this sum, this sigma, this term. Basically, this is summation over all the data, all the training points, right? Argument is the same. Right? The summation is the same. Only the internal part, this part changes, right? So when yi is positive, what happens? If yi equals to +1, what happens to this? This becomes, okay, in the geometric formulation, what happens? It becomes log of 1 plus exp of minus w transpose xi, right? Because your yi has become +1, right? So it becomes minus w transpose xi. What happens in the probabilistic part? In the probabilistic part, when yi equals to 1, this term stays the same. But if yi equals to 1, 1 minus 1 is 0. So this whole term becomes 0. Right? When yi equals to 1, this whole term becomes 0. So you're only left with this, which is minus yi log pi. So let's write that down. So what are you left with? Minus yi. So minus 1 into log pi. What is log pi? Log pi is nothing but log of, right? What is pi? Pi is sigma of w transpose xi, or sigmoid function of that. So it is log of 1 by 1 plus exp of minus w transpose xi. Right? This is the probabilistic one. So if you have minus of log of something, right, you can write this as log of 1 plus exp of minus w transpose xi. I'm basically taking this log this -1 inside the log. Right? When I do that, this gets inverted. Right? This internal thing gets inverted because minus log of x equals to log of 1 by x. Right? By just using this simple algebraic expression, I got this. Now, if you notice, this is same as this. Exactly the same thing. So when yi is positive, the geometric and the probabilistic equations that we saw here are exactly the same. Now the case 2. Now let's go to case 2. Case 2 is when yi is negative. When yi is negative, what happens? In the geometric formulation, yi becomes -1. yi becomes 0 in the probabilistic formulation. Right? So now let's go to the geometric formulation. In the geometric formulation, what do we get? We get log of 1 plus exp of w transpose xi. Because look at it. Look at this formulation. If yi is -1 times minus becomes +1. So what you're left with? Log of 1 plus exp of w transpose xi. Right? That's what exactly I wrote. Now let's look at the probabilistic. Formulation. In the probabilistic formulation, you have yi equals to 0. So when yi becomes equals to 0, this whole term becomes equal to 0 because you're multiplying everything by yi. And what happens to this term? When yi becomes 0, you're left with minus 1 log of 1 minus pi. So let's write that. What are you left with? You're left with minus 1 log of 1 minus 1 by 1 plus exp of minus w transpose xi. Right? Why is it so? Again, let's go back here. What? Minus 1, this becomes 0. So because yi equals to 0, log of 1 minus pi. What is pi? The sigmoid function of w transpose xi. Right? That's what I wrote here. Now let's play with this a little. Okay. So minus 1 into log of. Okay. So I'll just simplify this term here. What will I get? I'll get exp of minus w transpose xi by 1 plus exp of minus w transpose xi. This is what I got. Right? What did I do? I basically simplified this. Right? 1 plus exp of w transpose xi minus 1. So 1 will get cancelled. What am I left with? I'm left with this. The denominator stays the same. Right? Now, since I have minus 1, I can take the minus 1 inside and invert this whole thing. Right? Simple, because minus of log of x equals to log of 1 by x. Right? Using this simple expression, I'll invert this. So what do I get now? I get log of 1 plus exp of minus w transpose xi by exp of minus w transpose xi. Right? Now comes the fun part. Now if I divide numerator and denominator by exp of minus w transpose xi. Right? If I divide numerator and denominator by this, what do I get? So this is equal to, so this will become 1. So I'll get log of, right? I'll get log of 1 plus 1 by, because if exp this becomes 1 by exp of this will be left, right? 1 by exp of minus w transpose xi. Isn't it? Very, very simple. Right? Now remember, this thing now can be inverted. Now this thing can be written as log of 1 plus exp of w transpose xi. Right? Because 1 by e power minus x is nothing but e power x. Right? By using the simple expression, I got this term. So I inverted this. When I invert this, I take the minus, I convert it into plus. And what is this? This is exactly same as what I have in the geometric part. It's the same thing. This is my geometric part. This is my probabilistic part. Right? So with this simple, it's very, very simple. Using simple algebra, using very, very simple algebraic transformations, we have shown that geometric and probabilistic formulations of logistic regression are one and the same. So in some textbooks, you will actually find this formulation of logistic regression and not this form. But it's important to note that they're exactly the same thing. A lot of people get confused a lot of times. Some people say, oh, why? Actually, when I was teaching actually a classroom in person, some people said, Varma, when I go to Wikipedia or when I go to some sources, I don't see this formulation. I see something else. Then I had to actually work out the simple algebra. It's not very complex. Then I showed them that the geometric and the probabilistic interpretations of logistic regression are one and the same. Right? In some textbooks, you'll find this. In other textbooks, you'll find this. They're one and the same. As we have just shown here, a lot of times in machine learning, there are multiple ways to derive the same thing. So don't panic if something looks new. Try to work out the simple mathematics. Oftentimes, it's very, very simple.